Greetings from Jaya School of Architecture. We are today at the 26th session of this DECODE series, and today we have Engineer Rajendran sir along with us to do a very interesting presentation on the traditional architecture and native engineering. I now request Architect Bhavana, who is currently pursuing her MDes in SRM University, to deliver the welcome speech and the welcome note for the guest speaker of the day. Over to you, Bhavana.
Thank you, ma'am. First of all, I'm really honored to be doing this role of welcoming everybody to this meeting. It's really an honor. First of all, I would like to welcome our guest speaker, Professor Rajendran. A very hearty welcome to you, sir. And I would also like to welcome Professor Satish Kumar, Professor Anita, Professor Kavita ma'am, and all the other faculty of Jaya School of Architecture, and all of you who have joined in for the session today. A very warm welcome to all of you from Jaya School of Architecture. To briefly talk about Professor S. Rajendran, he has an experience of more than 47 years in the field of construction, graduated BE Civil from REC Trichy NIT, and postgraduate diploma in valuation. His professional experience extends from site engineer at Kalpakkam Atomic Power Project, assistant engineer in Tamil Nadu Highways Department to civil engineering consultant, valuer, specialist in cost-effective technology and native engineering. He is also associated with various institutions as visiting faculty. He is an active member of Heritage Screening Committee, Hindu Religious and Charitable Endowments, Government of Tamil Nadu. He has received numerous prestigious awards such as the Mamanan Rajarajan Award from Government of Tamil Nadu, Award for Excellence in Cost-Effective Engineering received from the Governor, Lifetime Service Professional Excellence Award, and Award for Exemplary Performance as Consulting Engineering. It's really an honor to have you here, sir, and I welcome one and all to the session. Thank you.
Thank you, Bhavana. We welcome you for this session, sir. The stage is yours.
Fine, okay. The topic today is the traditional architecture and the native engineering, right? What I am showing is the evolution of man, I mean the housing or whatever you call it. He started living in the cave, chasing out the animals which were living in the caves. Later, once he invented wheel, his movement started. Once he started his movement, he started building structures like a tent now, which is seen on the right top with sticks and poles, all those things, and he was able to do it something like a tent. And then the one which is shown at the bottom, he was able to construct with small pieces of stones, broken stones, and make something like a cave, resembling a cave. And that is how it started. Then all people are busy with making this something like a groin arch, what we name it later, groin arch, and with poles and other things started constructing. And another simple here, the one which is on the right side, you could see where my cursor goes. It's simply a triangle, the entrance. That in triangle, if we go for triangles, this is an isosceles triangle. If you're going for an equilateral triangle, that's much stronger. That is how our invention changed later. Most of the scientific equipments are, all have 3 legs, and all the 3 legs are equilateral. That's more stable. So then he started, after living in the cave which he made, later he started carving the rock and making something like a cave, which is in Mahabalipuram. You can see it is a carved portion. See here, our engineering science, where we say all the bending moment, point load, all those things doesn't work. Here, they've carved out all the negative spaces, and then you can see the column here and another column. All the ornamentation embellishments in this, all are done with that. It is a carved rock, a huge rock. They have carved it. So the carving also a traditional, system. We have done it. This is about nearly 3,000 years, to 2,500 to 3,000 years old. And later, see how the carving is done in a rock. You just see it. If we first take square or pieces, then that pieces are removed one by one, and then next another this type of squares, and again they get inside like this. They caved in. While entering, going inside, they've started leaving these things as columns. Then the columns were sliced or chiseled to get a pattern, and that pattern varied from style to style. Pallavas and then Cholas, you can name it. Those, they have their own style of doing it. Another one, all these things are Pallavas. Pallavas sort of predominantly, they have the line set. Over the line set, the column is placed. And this is another, they call it in the Palagai. This is also a part of, later Chola took this as a main thing, and they have done this. So this is a Pallava cave. You see how deep they've gone, how deep they've gone. And the whole thing is done manually, not with machines, not like what we have now. All the machines are available, but we don't make it. We don't do it because of time constraint. We have another material, great invention, concrete, so we can mold it. We are doing it now. See this, that all these things are done on rock outcrops. Probably in this area, there would have been a big rock hillock, and they have done it. See, to visualize this, you have to visualize the negative spaces first. Remove the negative spaces. Negative spaces means, what I mean is, you see the one which is at the top, this side, they have to remove it. Inside this side, they have to remove it. All those things you have to visualize and see the proportion. All the proportions are very perfect. That you need a very extraordinary skill. Our forefathers had that. Pallavas had that thing. We can proudly say they were all our forefathers. So they were able to do that. And that's why you and me are in this industry. Like I'm a civil engineer, you are an architect. We are in this. So we have some gene connection there. So this way they started thinking, shapes. And then this is only for the place of worship. They've done it. And here, what was the deities were kept inside later. Once they make it, this is also carved inside. Carving also, they would have done it like this. This is something like a pitched roof, pyramidal roof in a curved shape. Aesthetically, they've curved it, and see that proportion, how it is. See, another huge mural, one of the best murals in the world. This says bas relief. This is also done on rock. So carving, it is another system like art, fine art. This is something they wanted to express. They wanted to express their feelings. They wanted to express their interest of what they wanted to convey. They conveyed it in this. Arjun, Tabas, all those things they used to say. This has got a lot of detailing, but this is a carving. The huge rock, they've carved it on side. This one, and then they've made it. The mural, making a mural, they would have taken some time. I mean, time we don't know, maybe 2 years, 3 years like that. But many people will be working. The finer points are done. Fine finish would have been done by experts. So the initial rough work and all done by people. See, this is another comment. This tiger cave has become a facade for many exhibitions in Chennai. This is also a carving. That rock would have been up to this level. That would have been for about from this wall to end. That would have been about 3 meters or something. They have removed that. So this is one technique by which they are able to express the space and other things. See another, the same contemporary, same period, Karla Bhaja caves somewhere in Maharashtra. See this is also in tiers they have done it in layers. See, this is the ground floor, this is the first floor, this is the second floor. They have done, and they had staircase entry, everything inside this. And here also. So like this, they have done it. See, look at this. And here, see the half. Yes. Are you able to listen to me? Am I clear now? My voice is clear? Ma'am? Any one of you can respond? Hello?
Yes, sir.
Okay, fine. See, they have removed this portion, there is no pillar. See, here you have pillars. We think the pillar holds this, nothing. The rock itself holds it. So it is a totality. Whether you have a rock support here or not doesn't matter at all. So this is only a carving, a part of it. The same thing can be done in thermocol, similar to this, and see the single unit. So this is a single unit. See, inside it is something like a wood. It's not wood, it's stone. The carvings are done with stone. How fine they've done it. Just watch. See this also. See, the column has gone. Here the column has gone. Here the column has gone. But still the whole thing stands because of the rock. Monolithic. It's monolithic. You have removed it. They've removed it and it's still standing. It is like same thing can be done on a soap. Now our students can work on a soap and show this type of things, carving out. And this is how they have done it. Even the statues here is a bas relief. The stone would have been up to this thickness, this level. They've carved it. See here again, same thing. Different Ajanta caves, Maharashtra, here also. See, one thing you have to understand, the whole things were done without light, all in wig lamps, not with electricity. And even the daytime, it will be like a regular midnight dark, pitch dark. So they had worked on it with no artificial light. Only they had used wig lamp oil, and that when the lamp glows, it produces enormous heat also. So that and all they withstood and they have done it. And this is one of the beautiful examples for rock cut. See, this is in Arabia, Saudi Arabia. Soft stone, the stone density is very poor. So you can do it like something like a sandstone. Throughout the world, just I want to show you at the same time. This is in Bali. See, this has got some motifs which resembles Indian. This is the sculptors were trained by Indians and they done it. This one, Angkor Wat and all, you would have seen it, something like this. See another in the cave here, Iran. See, this is in Jordan. See the difference. The regular rock is here. The regular rock. Regular rock is here. That same rock texture that would have been here also on this, they have done it. They have done it on this and they have gone inside. They've removed all this rock and see the proportion. That time there was no paper, no laptop, nothing. They had done it. They had done it on with yellow ochre or something like that on the rock. So with a lot of constraints, they had worked and they produced marvelous structures. See, this is another one which we have in Tanjavur where I live. This is why I'm showing you the same rock. Once man started using this, he was able to lift it. And the lifting each piece in this, it is a tribated construction, we call it, stacked one over the other, same granite, and that granite, and see the proportion here, see the proportion, and it is done. The total height is about 60 meters. See, now I am coming to this. Yes, yes, ma'am. Anything you want to say?
No, sir. No. Absolutely fine, sir.
Okay. So this why I'm showing you this with this about nearly 120, 140 years old. I mean, sorry, 1040 years old. 1000 years back, we had the knowledge and wisdom of making this type of things. And this is, we call it tribated construction. It is done with small stones stacked over one over the other. That small in the sense that would have weighed about nearly slightly less than 100 kilos. Two persons would have carried it and placed it over that. And to the height of about 60 meters, they had a ramp all round. See here, about that ramp would have gone about angle of repose, if you calculate, around 600 feet. With the 2.5 rotations, helical thing, you can reach this level. This is about 60 meters. So all these things are made out of small in the sense about 1 meter by 0.4 or 0.6 or 0.75, another 0.75, that size of stones. The two people must have carried it with a pole and a rope hanging, the stone hanging on the rope. So that would have been the style of, that would have been the system of lifting, and they had taken up to that. And apart from that, there's a beautiful geometry in this also. So by the time the knowledge, that is why I wanted to say our native engineering, this is, they never did any any structural calculations we may not know. They have done it with some basic wisdom, and they are derived from the materials. That's on experience. And I would say normally, if you go for this type of precision and other things, my only answer is they have done it by divine guidance. That's the only answer I'll be able to give, because it is beyond imagination, this whole thing. And see the geometry here. Why I'm coming to this? I've seen the showed the evolution. Now rock cut, and after that tribated pieces of rocks are placed one over the other. Here in this temple, you see this. This is one of the best in the world. The geometry in this, well, you can call it what we study about. What do you call it? Modular coordination. It is a very good example of that. See, the height is 60 meters, and drawn an arc, you'll get 120 meters. This totally. You make a 120 square and draw the diagonals where it meets. It is a sanctum sanctorum. Exactly in this. See this. This one. And after that, the second triangle of the same size, where if you connect the diagonals, it meets at a Nandi Mandapam, what is existing now. The existing Nandi is different. That is done by Nayaks, but original Nandi used to be slightly much smaller, the same size as what exists on this place at the top. And see the entrance here. There are two entrances. One is the main entrance. They call it Kerala Vail. The next one is the second one, that is called Rajarajan Thiruvoyal. Thiruvoyal means main entrance. So in this, see the geometry here. 2.5 squares. And this is about 300 meters. 120, 120, 240 plus 60 meters, 300. 300 by 120 is the geometric, the whole campus size. And the one, this is the outside entrance. It is here. The base of the house, our main entrance matches with this. After that, there was a complete fortification done by Nayaks and Marathas. So those things are there. This is a Cholas construction, exclusively Cholas, about 1,000 years back. See the foundation. I am coming to the again. See what we see, the modern engineering, we say rough foundation. The whole thing is like the whole base. The existing foundation is only about 5 feet, 1.5 meter. and how they had prepared that. See, the first layer is laid in one direction. That is of granite pieces, the size of approximately 3.6 meter by 40 centimeter by 60 centimeter, placed in one direction. The second layer is in another direction. The third layer is again coming back to the first, odd courses and even courses. They had arranged about 5 courses over that the whole building, whole structure stands. This acts like a raft. Whatever load comes, this doesn't have any unequal settlement. And they have done it on a limestone. From where they got the knowledge? That is why I said the native engineering was very strong. They had all the basic things, and to assume, see what they do, olden days, even some of the villages still they do it. They'll excavate the whole foundation, not the walls, just below the walls. If they are going for a structure, they will excavate the whole area and allow it for one season. I mean, they call it 48 days, one mandala, and leave it, expose it to sunlight and expose it to rain. Then the whole thing settles. Then they start going in for foundation work. So like that, they had given a lot of time for each and every procedure. So that's how they have been doing it. See this, the reason why I said they have stacked one over the other, there is no mortar in between. There is no mortar in between. I am restricting myself with the temple construction, right? Even there's a secular building. I mean, you should understand, this is the best example, living example, 1,000 years old. We don't have a house for about 1,000 years old. We have houses for houses with about 150 years, 200 years, not to this extent, but still, this is a place where we could see there is no mortar in between. See how they have placed it. This is a cantilever, this is a counterweight, and again a cantilever, counterweight, like that. All these things comes in the temple grammar. Everything has got a proper height, proper width. All those things comes in their calculations. Their unit, they take the unit as the main deity in the sanctum sanctorum. That from there, all the multiplications starts. First, the whole sanctum sanctorum in this temple is about 24 feet square. So from there, the whole thing starts. See this, to resist the lateral movement, they have gone for tongue and groove. The thing that there is something like a tongue at the bottom and there is a groove at the top stone, so it doesn't move. There's another method they use it, a ball and socket. This is something like a semi-spherical ball, and there is a cup-like thing, it settles over it. The stones were placed one over the other like this so that to counter the lateral movement. இதில் அடுத்தது tongue and groove இந்த இது சைடில் cross section. அடுத்தது interlocking joints, all done in stone, mind you, not in wood. இவ்வளோ கஷ்டம், இவ்வளோ ரொம்ப சிம்பிளாக நம்ம டிராயிங்கில் நம்ம ட்ரா பண்ணிடுறோம். But what you see there is, amazing, the work. It needs a lot of calculations. In paper you can do it, in wood you can do it, but stoneல எப்படி பண்ண முடியும், கிரானைட்ல ரொம்ப மார்வலஸ். அதான் இன்னும் நாங்க every day, whenever I enter the temple and go around, I see a new thing in that. See this, the ball and socket are an exaggerated drawing. This is how it stands, the whole stone. No mortar in between, mind you. And they have understood the basic structural principle of loose joints. See, that is a loose joint. Even in a tremor, when there is a mild tremor in that, it gets settled. The small space movement it gives and then settles in that. So that is one of the highly technical knowledge point. If you have a loose joint, it doesn't fall immediately. It will accommodate the shock and adjust and then do it. See, coming to this, one of the mandavas here, that why I've taken this, I'm going to explain you a very simple principle of how the column stands, how the columns, what we are doing now. See the difference here. See, this is a column, independent column. freestanding column, you can call it. The column is from here to here. And it stands on another rock, a rock bed. It's a bed block, you can call it. And it stands freely without any connection. And there is another block here. This is a bed block to take the load of this beam. And this is embellishment or an ornamentation which gives beauty to that. They could have left it like this, but they would not. They have used these motifs. It is something like what you call it, in the banana flower. See this, they call it. See, this is how. See the column size at the bottom, column size at the top. There is a small difference. So the top is slightly smaller than the bottom. That itself makes it stand. Purely on gravity, it stands. Nearly about 650 years. This was built by Nikes. 650 years and the column loose joint. But how we do the column now, modern engineering, we dig it in the foundation. In the hole, we dig it down and go down and make a footing broader. Other than the steel rods, so we bring it through the column to the top. The column is continuous from the foundation. We say load gets distributed along the thing. But here also the load gets distributed without any connections from one element to another element. That's a great thing. See, this is top is a bed block which brings the load of this half the beam to this side and half the beam to this side. And half the beam takes the other half of the slab load. So all the load comes to this portion, all the load to this half, and the beam load comes here. So that is transferred through the bed block to the column, and column brings it down and takes the floor on the flooring. It is only a flooring where we walk. If you pour water, sometimes the water comes out in the other side also. So there is no mortar in it. There is a thin film of gap, but it stands. Some places it gets stuck and they have a ball and socket arrangements in that. See the column. See, those days, making a cantilever is very difficult. In a stone, whatever the size available, the stone was available for about maximum 3.6 meters. That's about 12 feet. 12 feet length slab. How to rest it? If in the காலத்துல ரெஸ்ட் பண்ணணும். இந்த காலத்துல ரெஸ்ட் பண்றப்போ இந்த காலத்துல cantilever எப்படி பண்ணிருக்காங்கன்னு பாருங்க. This is a cantilever portion. The column, the slab comes and rests here. Small slabs. This is a separate piece. This is a separate piece. The one at the top is a separate piece. And here, this is a separate, the whole thing up to this is a single piece. Every calculations. The load is actually transferred in the line load. It comes to the column. Column base is wider. And the cantilever is shared here. And then it comes to this point. See this support here. It is only a support. They could have left it like this straight up, rock, but they have made it a beautiful ornamental work to simplify that. And another, see the cantilever, stone cantilever up to about 2.1 meters. 7 அடிக்கு பண்ணிருக்காங்க cantilever. இது ஒரு பெரிய engineering marvel இதுல. எப்படின்னா இந்த corners it is radial. இந்த கார்னர்ஸ்ல எப்படி இருக்கு பாருங்க 90 degrees இந்த இதுக்கு அப்படியே ரேடியலா இருக்கு, இங்க ரேடியலா இருக்கு, இந்த இடத்துல ரேடியலா இருக்கு, சென்டர்ல ஸ்ட்ரைட்டா இருக்கும், இந்த சைடும் அதே மாதிரி இந்த ரேடியலா இருக்கு. It is angular, but the piece at the bottom, the connected piece at the bottom will be a single piece. So இதுல இருந்து இது வர்றப்போ அந்த மேல இருக்கிற இது மட்டும் தான் ரேடியலா இருக்கும். பட் இது ரொம்ப engineering aspect. Forget it if you are not இதுக்கு இன்னொரு படம் காட்டுறோம் பாருங்க. Look at this, how it is. It resembles wood. It's not wood. It's a rock. To reduce the self-weight, they have removed this. At the same time, they don't want the stone to break in cantilever. So it is something like a beam they had given. Rib, they have increased the rib. The same technology used in automobile. A plain sheet of metal in an automobile, a body. Once you jam it, it gets caved in. it loses. But once they fold the sheet outside with some ridges, and if you bang it, it will retain. So something like that. These are stiffness. They call it stiffness in mechanical engineering. Here also, these are the stiffness so that the stone doesn't break. இது ஒரு பெரிய engineering marvel. 1000 years முன்னால பண்ணிருக்காங்க. Not இப்பெல்லாம் இருக்கிற, we have with so much supercomputers to calculate all the complicated theory, calculations, but here they had done it. What calculation they had, what type of calculation they had done, unimaginable. We are not able to decipher. We are not able to come to a conclusion after seeing this type of wonderful things. Still there is a gap. பாருங்க எப்படி இருக்கு இதுல 1000 years அந்த gap இருக்கு அப்படியே. It is a separate piece and this is a separate piece. Still it stays together. இப்படியே இருக்கு. இதுல நான் ஒரு இது மாடர்ன் டெக்னாலஜி சொன்ன ஆங்குலர் ஃபிரிக்ஷன். They had employed the technique of angular friction. Angular frictionங்கிறது இப்போ மாடர்ன்ல ரொம்ப பெரிய லெவல்ல பேசிக்கிட்டு இருக்கோம். இந்த இதுல வெரி சிம்பிள் இந்த ப்ரொஜெக்ஷன் கேன்டிலிவர்ல பண்ணிருக்காங்க. ரேடியலா இருக்கிறதுனால இட் won't fall directly down. அப்படியே ஃபால் வந்து டைரக்டா இருக்காது, ஆங்குலரா தான் இருக்கும். பட் உள்ள இருக்கிற அதோட கவுண்டர் வெயிட் வந்து ஸ்ட்ரைட்டா இருக்கும், அதனால விழாது. இத பாருங்க how it is done. See the cantilever. You know the distance இப்போ இதுல இருந்து இந்த இடத்துல இருந்து ரொம்ப unimaginable height. இந்த பாருங்க இந்த இடத்துல இருந்து இந்த பாயிண்ட் இது வரைக்கும் பாத்தீங்கன்னா இட்ஸ் about 2.1 meter, 7 feet cantilever on stone. இதை எப்படி வச்சிருக்காங்க பாருங்க. இந்த இதுல இது this acts like a fulcrum. இதுல சப்போர்ட் பண்ணி இந்த பீம் ஹோல்ட்ஸ் this அண்ட் இந்த பீமை சப்போர்ட் பண்றதுக்கு இந்த கீழே இருக்கிற காலம் சப்போர்ட் பண்ணுது. இது ஒரு horizontal cantilever பீம்னு வச்சுக்கலாம். This is a separate member, this is a separate member and they have placed it. இது செப்பரேட் மெம்பர். இந்த உள்ள இருக்கிற இந்த பென் டீடைல்ஸ் போய் அது ஒரு கவுண்டர் வெயிட் இருக்கும். So the whole thing done in a basic principles. How many of you seen the balance in about ஒரு 60-70 இயர்ஸ்க்கு யூஸ் பண்ண பேலன்ஸ் எல்லாம் பார்த்துருக்கீங்களா? ஆர் இப்போ ரைஸ் பேக்ஸ் எல்லாம் இது பண்ற பேலன்ஸ் பார்த்துருக்கீங்களா? பிளாட்ஃபார்ம்ஸ் எவ்ரி ஸ்கேல்னு சொல்லுவோம் பேலன்ஸ். அது எப்படி இருக்கும்னா இதே மாதிரி தான். அதுல லாக் ஸ்கேல் மாதிரி இருக்கும். They'll keep a big bag of rice about 75 kilos. அந்த மேல இருக்கிற அந்த பூமை வந்து ஒரு கவுண்டர் வெயிட் அப்படி அட்ஜஸ்ட் பண்ணுவாங்க, ஹரிசான்டலா வரும். அந்த they have the markings, gradings வச்சிருப்பாங்க. They'll tell you the grade, what is the weight of the bag. அதுதான் பண்ணுவாங்க. Same principle they've adopted. See, this is a fulcrum. This is a fulcrum. இந்த லோடு வந்து டோட்டலா ஆக்ட் பண்ணுது. இந்த இடத்துல fulcrum. இந்த பீம் வந்து brings the load to this point. This load goes to this and supported. So this is how the whole cantilever stands. இது சாதாரண கொஞ்ச நெஞ்ச நாளா நிக்கல, 1000 வருஷமா நிக்குது. See ஒரு ஆங்குலர் கார்னர்ல பாருங்க. கார்னர்ல இருக்கிறது எவ்வளவு பர்ஃபெக்ட்டா இருக்கு. இது 90 degrees. இது 90 degrees, is 90 degrees, is 45 degrees. இதுல இந்த பீஸ் மேல இருக்க கேண்டிலர் இது நான் இது ரொம்ப நேரம் ஐ எம் ஸ்பெண்டிங் பிகாஸ் திஸ் ஒன் ஆஃப் த கிரேட்டஸ்ட் engineering marvel of ஆர் இது இந்தியால இருக்கிற இதுல. லுக் அட் திஸ். அப்படியே ஒரே பீஸ் இது ஸ்டோன். இதுல இருந்து இந்த ஸ்டோன் ஒரு பீஸ். அது மாதிரி ப்ரீகாஸ்ட் மாதிரி இப்போ வந்து அதை ப்ரீகாஸ்ட் நம்ம சொல்லிட்டு இருக்கோம். ஒரிஜினலா இட் வாஸ் டன் பை ஹியூமன் பீயிங் வித் ஹேண்ட், மேனுவலா பண்ணியிருக்காங்க. மேனுவலா செசில் பண்ணி இதை ஃபிக்ஸ் பண்றது வந்து எவ்வளவு கஷ்டம். இப்பெல்லாம் மெஷின் இம்மீடியட்டா வித் ஃப்ரீ ஹேண்ட் டூல்ஸ் எல்லாம் இருக்கு, அப்ப இல்லை. ஸோ எப்படி பண்ணியிருப்பாங்க அதுதான் இது. இந்த நான் சொன்ன இது வந்து மேல இந்த டெம்பிள் வந்து டோட்டலி கேவிட்டி, ஒரு இன்வெர்டட் டம்ளர் மாதிரி இருக்கும். இதுல வந்து ஒரு இன்வெர்டட் டம்ளர் மாதிரி இருக்கும். இது இந்த டம்ளரோட it is wider at the base and narrow at the top. Lateral wind forces எதுவுமே இதுல ஒண்ணுமே செய்யாது. That has got a resistance from the shape. The shape itself protects the whole base temple. கீழே இருக்கிறதெல்லாம் பாருங்க how the walls are done. Wall and socket. இதுல we had done calculations. இப்போ மாடர்னா நாங்க calculate எல்லாம் பண்ணோம். பண்றப்போ இந்த இதோட லோட் பேரிங் கெப்பாசிட்டி ஆஃப் த சாயில் வந்து It's only now only 1/4 of the weight it is acting on it. It can take another 4 times more than the load, what is the existing load. So on the calculation of soil mechanics, எப்படி பண்ணாங்க என்னமே தெரியல. இந்த இது பாருங்க 47.4 tons per meter square, and the load which comes, the resistance from the soil is only 162 tons per meter square. So nearly 4 times it can take, the soil can take. So they have chosen the soil in such a way. இப்போ இந்த இடத்துல இவ்வளோ பெரிய டெம்பிள் இது வருமாங்கிறத கல்குலேஷன் பண்ணியிருக்கணும் முன்னாலேயே. அதோட டோட்டல் வெயிட் அசியூம் பண்ணிட்டு அந்த வெயிட்டை இந்த எந்த இடத்துல பிளேஸ் பண்ணலாம்னு chosen the soil also. இவங்க சூஸ் பண்ணியிருக்க இடம் வந்து ஒரு லைம் டெபாசிட் அந்த இடத்துல பண்ணியிருக்காங்க. இப்போ சில ஃபவுண்டேஷன்ஸ்லாம் I have seen when we have opened it. It has got a combination of granite slabs with a brick inside இருக்கும். இது ரொம்ப நீங்க ப்ரொஃபஷனல்ஸ் இப்போ உங்களோட குவாலிஃபைடு ஆர்கிடெக்ட்ஸ் இவங்கெல்லாம் இருந்தீங்கன்னா இட்ஸ் wonderful thing to learn. Angular. In angularல whatever the foundation you do, the load gets distributed like this, not this way, not along the joints. இந்த இதுல வராது. So this is a wonderful system they had adopted. Now I had done it in one of the renovation of a temple in the same principle, and it is great. I mean, it's able to take all the load. About 45 degrees. See, look at how the wall, one stone is placed over that in 45 degrees. I have marked it here. Look at this. So the load doesn't, whatever the load comes, it gets distributed throughout, and the throughout one again goes to the bottom like this. So once it goes down, it will be minimum. See the plan here. At the side of the right hand side of that. Look at this. This is a plan. This is a view. And this is another view. Foundation. See some of the existing structures. We have all precast. This is removed. You can remove piece by piece from top. Again, reassemble. Once you do that, while removing, they'll do the markings here, numbering, and then they can replace it. See, this is one of the Marathas' work. See again, above plinth up to lintel. See, look at this, separate beams, and then over that the cantilever. Look at this, how the cantilever, single piece up to that, it stands on that. See, this is a brickwork. Have you heard about brickwork cantilever? Look at this. Bricks are extended in a pattern like this. This is a cantilever, one brick and goes like this. Only brick cantilever. They had such a beautiful technology to use it. That is why we say all these things are, even though it is a tension member, it stands on compression. In fact, whatever load comes over it, it's only a compression member. It's converted as a compression member. So this compression member allows whatever the load which comes over it. So even the load comes over it at the cantilever here, it will be like a compression member only, which is attached. Surface tension, it stands on surface tension. The mortar is fixed on the brick on the sides and place. For this, they'll prepare a mold at the bottom, and over the mold, they'll go on placing the bricks like this. And after setting, they'll remove that. The whole thing was possible in, there is no steel, no foreign body in that. In a cantilever, they had done it with brick. This is a Marathas work. See the same work what we do now. We are many places, all the compression compression members, they were using steel. You don't need it. For a compression member, if the curve itself takes the load, arch, what is the arch? Arch is a compression member. Whatever load comes over it, that is transferred through this side. See, this is a 9-inch. If you do it with compression members, then your cost of the house will be less. See this, I have used something like granite. No joints. The mortars is only lime mortar in between. Lime, jaggery, and then some more we had used very well ripe, plantain fruit. And see this, it stands. Initially, you have a formwork like this, start doing it and do the construction at the top, then remove this, it stands. Very simple. All the compression, I don't think as an engineer, as a basic principle, we cannot accept that. Why do you need a steel? Once you put a foreign body inside, again, it actually corrodes, gets corrodes, corroded in that, and it swells, creates a lot of problem. So in a compression member, you go for only the natural materials, use it in the form of an arch or a segment of an arch, it will stand. See this, a dome, octagonal dome. You can see underneath, octagonal dome. Brick, everything is done with brick. See how it is done. Very simple. See, this is a dome. We can do a dome. Once you do a dome like this, an elephant can stand on it in a 9-inch or 4.5 inches dome, because the load is transferred down to it. The best example is a basket, bamboo basket. You can see when they make a bamboo basket, they do it with individual elements, and one method of doing it. I think I've given the basic principles. See this, one of our good architects, great architect Ramalingam is inspecting one of the sites. We have done it with lime mortar and we have placed it. See, there's no steel in this whole structure. This is myself. Oh, this is, see the curve. See from here it is a 2-point arch. From here we take this radius. From here we take this radius and it converges. From here you have a threaded wire, and here, and you go on keeping the brick in the same inclination as the wire travels, you get this, it is converging. See, look, we need only a guide like this. See this, it is converging. And here the springing of that place, we have done it with the squinches. Squinches we have done with the granite. With the modern machines, we have cut it to the required curve, and then we have placed it. The load is distributed on this. See, one of the temples, about 850-year-old temple, was renovated like this. See the existing one, see the bricks, how it is interlocked. This is also about nearly 800 years old. Look at this, how it is done. So, but one great thing, a bad thing, what they do is, after when they do the repair, they do it with cement. They have plastered it with cement. They should not do it. They go for lime mortar. See, for students, we teach how to make a dome. I think this is how the temple roofs are done like this. This they call it wall. The wall also, it's a two-walled wall, and in between it is filled with granite and lime. We call it the diaphragm wall, this wall. Over that, there is a bed block, small projection. Then here another projection. Over that, they have this type of stones. They call it in Tamil, pavkal அப்படின்னு சொல்லுவாங்க. And this is about 1.5 feet width and height about 9 approximately. The length is placed, and over that they put lime mortar with screed, like a small surki. Then they make it level at the top. This is how the temple walls are done, traditional temple technology. See, look at this. We had used even bricks, combination wall. Combination wall. There's a stone and then brick, stone and brick, stone and brick. I have seen it in about 850 years old temple. This is an inside. This is, we call it corbelling. And all the joints are straight. It's not straight. We call it polygonal joints. The joints are like this. Whatever the stone, whatever the size they got, they placed it. And this gives a lateral movement resistance. Octagonal dome. The whole temple at the top. This is same thing, a combination with mud. And we done a government work building. A combination of the Rajarajan wall and a 4.4 groin vault at the top. We have done it about 5 years back in Tanjavur, Tamil University. Right. Now coming back to that, I'm going to show you some of the bricks. This is a place where you all can search in a Google Earth near Pudukkottai, on the eastern side of Pudukkottai. You see a place, something like a crater in the moon. This is a very old settlement of 2000 years old Chola, early Chola dynasty. This is a huge bund you can see all around. It's something like a lake. It's not a lake, fortification. And the whole town was inside. This is about 30 feet height. Still we can see it east of Pudukkottai. And there we got some very good samples of brick. I'll show you the bricks also. See at the top, this is a huge chariot can go on that. This is about approximately 12 to 10 feet at the top. And this height is about 30 feet from the ground level. And see the brick, how it is. All huge bricks were seen on this, on the top. The brick sizes. Myself and Kodavoil Balasubramaniam, another great authority, a great authority in Chola dynasty. He's a guy who's still living in Tanjavur. We too, I'm very lucky to have him here, and I learned a lot of things I learned from him. And he's one Dr. Kodavoil Balasubramaniam. He has written a lot of books on the Cholas. So we went there once, and when we went there, we took a photograph. See, this is a pathway. See, brick, you see huge bricks. See the brick. See the pen there. What is the size? It's about more than 15 inches by 11 inches by 3 inches. Can you imagine a brick of that size? It is there. See this. We removed some of the bricks from there. See that. It's about 915 inches length. 11 inches width. See a Lamy pen, what size. See the brick, normal brick, what it is available in market. See the size. See how small the modern bricks looks. See the thickness is nearly same. This is another brick, thinner brick. Thinner brick. See the thickness is very. Why do you go for smaller, thinner ones? That will, due to surface tension, that will stand. The load is easily transferred from one brick to another brick. If it is thick, the mortar thickness, it won't be, the load transfer will be, there will be problem. So this mortar, they have a special mortar. They call it, they grind it with lime and sand. They grind it, add some nutmeg juice, jaggery, all those things, and then make a very good paste. See, this is a quarter brick on a circular column they had used. See, we had prepared the same mortar from one of the literatures available in Saraswati Mahal. The combination, we had done it with, we have ground the sand and lime, and the thickness of this mortar is only about 2 mm. That in Tamil, they call it Sagadam Teital. The rendu brick surface tarela grind manite, plain or apply a 2 mm thing and then just stick it. Up here. Look at this cross section. So if you wish to control the future, study the past. That's in architecture, and many architecture students must be seeing it. You have a very good, especially in South India, jokingly used to say, you as a student study more of British history rather than Indian history. We have more in history. We have lot of standing examples. You can take a class taking them to a temple or a mosque or somewhere nearby and show them and explain all those things. But British history, I told you, some of your colleagues also in Council of Architects, I told them, I requested them to go in for more of Indian context, go for South Indian context. You have a lot of things there. But anyway, that is my thing. There is no limit to the future achievements in the fascinating field of human activity in which the art of architecture and the science of engineering work together to improve the way in which man lives. And here, one thing very simply, the native engineering, there is no tension member. If you avoid tension member in a construction, especially the cost-effective buildings, the cost will be very much less and the huge amount will be saved. So that's why that is the gift given by our forefathers. That's why I call it a native wisdom. A great thing. They had done it with a lot of compression members. I think I wanted to convey this. I took this opportunity to talk about this. But anyway, how far this has impressed you, I don't know. But I'm satisfied. What I wanted to say, I conveyed. That's thing I have. And this is the standing example of all this technology in one structure is this big temple in Tanjavur. What all I said is there. So one technology, one structure, which has got so much of traditional technologies, and it still stands without even a single crack for the past 1,000 years. That one thing is enough. In science, we say we have to prove it. This is the proof. What proof you want more than this? That is why I'm very particular about giving the knowledge. This is one thing which everybody should see, and every architect, every architectural student should come and see this temple, and you get inspired and think of your try to save some of our traditional monuments and all the valuable. Our heritage tells about our culture. So that's very important, learning heritage and doing it. So I think thank you very much for giving me a very golden opportunity to talk to young brains and some of the experienced professors. Any questions you can ask me.
Thank you, sir. Thank you for such
Welcome.
an insightful session. It was so nice to learn about our traditions, sir. I hope this would be of great help to all the students and professionals, academicians here. Thank you for an awesome session. I request the participants to post your questions in the chat box. Meanwhile, I request Architect Abdul Rahman, who is associated with Ali Muhammad Salik Academy of Architecture as an assistant professor, to deliver the vote of thanks and a few words for the guest speaker of the day.
Good day. We hope you all have a very good evening. On behalf of the organizing committee and the audience, it's my immense pleasure to thank the speaker of the day, Engineer Rajendran sir, for all the valuable info he shared regarding the traditional architecture and native engineering of various places like Mahabalipuram, Tanjore, etc. Thank you, sir. It was very informative.
Welcome. You are welcome.
I also extend thanks to the participants for their cooperation of Jaya's DECODE series. Lectures like these cannot happen on a sudden. It requires planning and bird's eye for detail. Here we are fortunate enough to be led by a team of a very dedicated and a motivated team of Jaya School of Architecture who know their task and are very much result oriented. Thank you, team, for providing us a DECODE series. Once again, I thank all for your cordial cooperation. Thank you.